Hello, testing. Can someone help close the red door? Yeah, thank you very much. Is the sound okay here? Seems like a large echo here. Okay. I think few of us will not be here because of other courses. So this is just a replacement. So I won't be harsh on your attendance. I know some of you couldn't make it. But the school requires us to do physical, so no choice. So we have to come to class, even with few of you. Anyways, I will do recording. Yeah, as usual. Okay. For your assignments, I think I'll finish by today. So I will give you back tomorrow, and we can discuss solution. And I think assignment 4 is posted, right? But it won't be accessible, so you could try and practice because it's very useful for the exam. We will post solutions by this week as well. And if you try the tutorial, I encourage you to try the tutorial question because in the last day, I guess we will discuss some of them. Okay, especially for those you think that are very hard. Okay, we can discuss together. Yeah. So today is the first replacement class. For the second replacement class is on Thursday 9 to 12. Where's the place? Where's the place? Anyone know? A4 108. Okay, A4 108. I posted on Moodle. Please check the announcement. Yeah. Okay. Any question from last lecture? No? Okay. So let's recap on some concept that we have gone through last week. Basically, two very important concepts that come parallel is one of them is decimal expansion. The other one is continuous fraction. Well, we just look at one example that we know, right? For example, we work on square root 2. Okay, if you press your calculator, you know that this is 1.414 something. Okay. On the other hand, we can write it as in a continuous fraction form, which is 1 plus 1 over what 2. Is it 2 plus 1 over 2? Is it this pattern? Okay, maybe you can check. Okay, exact value doesn't matter, but then we want to know how to get this. Either you want to get these decimal places, right? Or you want to get this partial, what do we call it? Partial denominator, right? Partial denominator. Okay, so what's the formula to obtain them? Okay, so for the first one, okay, so remember what do we do? So we will set Ci, okay, to be gamma, the flow of gamma I, and your gamma 0 will start with the original term. Or if I set this as our alpha, then this is the alpha. Okay, so you read out the integer place, and then what do you do next? You take this gamma I, take away its flow, and then shift out by n. Okay, so that you can read the next decimal place. Does it make sense? Then you will read the flow of this again, and the difference, shift out by 1, you can read the still remember this process here? Maybe I can write it for you for this example. So if you set it as 1.141, right? So your C0 will be just 1, okay? And then your C1 is what? 10 times gamma 0 minus C0, which is taking the original term, take away its flow, okay? And then shift out by 10. So maybe I can write it here. So this term is 10 pi gamma 1, gamma 0, sorry. So 4 plus 1, 10 pi 0 0.414. So you get 4.14. And then we read the floor. The second. Yeah. So what we can observe here is what we did was when you take this difference, right, you make the difference in between 0 and 1 because you take away. So if it is in between 0 and 1, we shift out by 10, it will be in between one group, one group and because you have got then we bring out the floor, then we can read the distributions. Okay, how about the second one? Okay, how about the second one? What's the formula of this? Okay, so similar idea here. Okay, how to work out the partial denominator here. So similar idea here. So what we did was we'll set AK. Okay, so this we will call them like C0, C0 dot C1, C2, C3. So that's why these are the formula for this CN here. And on the other hand, this one we term it as A0 semicolon A1, comma A2, blah blah blah. Okay, so we want to give this formula. So A0, AK here, again, is a floor of something. Okay, so what's this thing here? So this thing here is termed as 1 over alpha k minus AK. Okay, so maybe we can see how this works in this case here. So if you set A0, okay, what's A0 here? Basically, this is floor of alpha 0. So meaning you need to start with alpha 0 first. Again, we will let alpha 0 to be the original term here. Sorry, alpha 0 equals to this alpha, which is square root 2. Maybe I use this color better. Okay, and without calculator, we don't know it's 1.414, right? So there's a very primitive way to do it. So we know that we can squeeze 2 in between 2 perfect square so that we can squeeze square root 2 in between 1 and 2. Okay. And so this one you can do without calculator. Okay, so this is good. Okay, so in this case here, your alpha 0 is just 1, okay, because it's the largest integer. Okay. Because the next one is already greater than 2. Okay. Yeah. So you can work out what is A1 in this case. So A1, so sorry, A1, yeah. A1 will be equals to floor of alpha 1. Okay, but what is alpha 1 here? Definition, you take 1 over the previous alpha 0, take away AK. Okay, so alpha 0 take away AK. But our alpha 0 is the original term, which is alpha, which is square root 2. And then AK here is A0. Okay. So A0 we found is the floor of square root 2. So it's minus 1. But then if you play around with conjugate, this term will be just what? Square root 2 plus 1. But then what's the floor of wait, let me check. Okay, so it's the floor of this thing, right? So in this case, what's the floor of this guy here? Okay, so the floor of this guy is 2 because we know that we can squeeze square root 2 in between 1 and 2. Then we can squeeze square root 2 plus 1 on both sides. We can squeeze it in between 2 and 3. Okay, so you repeat Okay, we will repeat for our A2. Does it make sense? Okay. So what can you see here? Did you see the similarity between these two methods here? Okay. So both of them involve taking difference, right? Okay. Both of them taking in difference, and then the first difference here already make this term in between 0 and 1. And so this term here is squeezed between 0 and 1. Okay, but then then this term, how much this term is alpha k minus a between 0 and 1. Yeah, so in this term here, it's also in between 0 and 1. Okay. Then so if you take something greater than less than 1. Okay. So if you take this reciprocal, what do you get? So if you take, okay, so let me write down alpha k minus a k here, which is alpha k take away x greatest integer less than it. This thing is less than 1. If you take the reciprocal, should be greater than 1. And then we take the float. Yeah. And then we take the float. Are we sure that this guy is less than 10? Or it is possible to be greater than 10 because we have an example looks like this. It is possible that your floor could be very large because we have this example. Let me show you. Okay, let me show you. So I think we didn't really verify it. I just tell it that this is the continuous fraction for pi. So that number there could be very large. Always in between 1 and 10. Okay, so this integer here could be really large. Does it make sense? Okay, yeah. So it doesn't bound, it's not bounded above. Could be something very big than 1. Okay, so far. So far, any question? Do you still remember what's the advantage of having continuous fraction? What's the advantage? Yeah, what's the advantage? Why do we do continuous fraction? Why not just decimal? Sorry? Convergence? Yeah, so we have the k convergence sum go option. Okay, but decimal actually also got k convergence by just looking at the truncated decimal extension. We also have the more than that. Maybe about expression. How do you express fractional number? For example, for decimal extension, right? Sometimes you need infinite decimal extension, but it has to be periodic. But then for continuous fraction, if it's rational, it's always you just need finitely made number to represent. That's not infinite. Yeah. Yeah. Okay, so this is one of the very good stuff. Yeah. Okay, convergent, K convergent is another thing. Yeah. Okay. Good. Okay. So far okay. So good. So far so good. Okay, so make sure that I give you a real number. You can either use decimal extension or you can use continuous fraction to find it out. Okay. So we'll continue with this last part of this chapter. It's about periodic continued fraction. Okay, so for example, just now you see that the square root 2 is that it's a periodic pattern popping up. Okay, so we want to ask when does this happen? Okay, when you could see a periodic continued fraction. Okay, well, so let's say if I give you this chunk of periodic continued fraction. Okay, so how on earth that you can figure out what value is this? So we're gonna play the same trick that we play on decimal expansion. Do you remember there's a trick we play with decimal expansion that has periodic pattern? We replace the pattern with the same terms, right? Okay, so in this case here, so where's the repeating pattern here? So you can see that this 1, 2, 1, 2 is keep appearing. So let x be 1 semicolon 2 comma 1 2. Okay, so there's a details here. One is the part, so we put a second. The rest we put a comma. So the pattern is 1 plus 1 over 2 plus 1 over x. So if you recognize this part here, maybe I can highlight it. Okay, so if you look at this part, it's the same thing. Okay, so but if you start at this part, it's not right because this one is start with 2. Okay, so your number here start with 1. Okay, so from here, again you play the algebraic trick. So you take x equals to 1 plus x over 2x plus 1. Okay, you make the denominator the same. Okay, so surprisingly, what do you see is you get some sort of a quadratic equation. You get some sort of quadratic equation, and then you found out that this term here will be either, so you use the formula. Is everyone okay with this formula? Should I recall for you? Minus b plus minus square root b squared minus 4ac. Is it okay? Everyone with this quadratic formula? Okay, any response? Is it okay? Okay, good. Okay, so we just straight away use that. So in this case here, you get 2 plus minus square root 2 over 4, which is 1 plus minus square root 3 over 2. So which one is true? Can't be true, both of them, right? Both of them are different numbers. Which one should you pick? Positive one, right? Because negative one should be negative number. Okay, so because there's no negative numbers here, right? Negative part. So this guy should be positive. Okay, so far so good. Okay, so I want you to see this observation. If you have this periodic pattern here, it can solve some quadratic root of some quadratic equation. Okay, so far so good. Okay, so I mean you could sort of see this quadratic, right? Coming from these two axes here. So one of the axes will appear at the middle. So when you move it up to the square, you get a square. Okay, so now we're going to introduce something called the quadratic irrationals. Okay, so this is a special kind of irrationals. So in irrational numbers is called quadratic irrational numbers if alpha, that irrational number is a root of some quadratic polynomial with integers coefficient. Okay? You just need integer coefficient. Okay, it's a very good properties here. And next theorem you could prove is a real number alpha is a quadratic irrational number if and only if they are integers a, b, c with b greater than 0, c non-zero, okay, such that b is not. And then arrange the three terms. So you can see that when you always see this c not equal to 0, always refer to that number as in the denominator, because the denominator will be 0. And then the conjugate of this will be defined as a minus square root b over c. You just change the plus sign or the minus sign is actually b times the minus. You guys learn the complex number a plus bi. So conjugate of a plus bi is a minus ci. So you just replace the sign at the square root minus, or the sign at the imaginary root minus. Now, why do we call it conjugate? Because if you multiply together, right, compare this two things together, the square root term will be square root term. If you learn more in mathematics, right, this will give you the length of this. And because you get a real number, a real number represents some length. Okay. So far, okay. So far. So I think this subtopic, right, we will just focus on quadratic irrational. Meaning irrational number that solve some quadratic polynomials equal to 0. Quadratic equation. Okay. Let's see what's next. All right. Maybe we can do some simple exercises here. Yeah, maybe we can do some simple exercises here. Okay. So first thing first is the reciprocal of a quadratic irrational is a quadratic irrational. Second is the sum of a rational number with a quadratic irrational is a quadratic irrational. Okay. So we're not gonna work with the definition, but we were gonna work with this theorem here. Sorry. This theorem. Okay. Because this theorem kind of categorify what this roots looks like. It looks like something plus 12 divided by some number. Okay, so we're gonna work with this. Okay, as long as it is a quadratic irrational number, this. So far, so good. Okay, right. Maybe I do one, and then you do one. Okay. I let you choose. Do you want me to do A or B? A or B? A, yeah. Okay, so I'll do A and then I'll let you try B. Very simple exercise, algebra exercise. Okay, so in this case here, we will let our alpha be some quadratic irrational. Okay, and then we just see what's the reciprocal of this guy. So meaning take 1 over it. So take 1 over this guy here. So you get C over A plus square root B. So if you want to prove that it's a quadratic irrational, right, you want to write it in this form. A as some square root and then minus. But then now the square root goes to the bottom. Is there a way like move it up? Yes. Okay. So that's what I said just now. If you take conjugate, multiply the conjugate, then this term, the product of this with conjugate will become some number again. Okay. Some real number again. Okay. So I think this trick we also played it when we calculate the continued fraction just now, right? Okay. So this is a very standard mathematics trick. Okay. So in this case here, what do you see? Okay, you see AC minus C square root B over A square minus B square. Sorry, B, thank you very much. Okay, A square minus B. Oh, hello. Okay, so well, I think we have to check whether these things are verified or not, right? So, so does this final term here satisfy these properties? First of all, b greater than 0. First of all, b greater than 0. Okay, so I mean, well, let's bring this condition down. Maybe we can verify it. Okay. Yeah. Okay. So there are a few things to check, right? One of them is the thing inside the square root should be positive. And C here, we want it to be non-zero. That's it. So, what do you see there? What do you see here? What do you see here? So, is it possible to make this term here in terms of square root? C square b? Okay, very good. Okay, we can make this into c square b so that I can push everything into the square root. Good. Is c squared greater than 0? Huh? Must be. Why?
It's because b is greater than 0.
Then
C squared is greater than 0 because c cannot be 0.
good, very good, very good. Okay, very good. So you see, c is not 0, right? And so it could be negative or positive, but after square, what happens? Must be greater than 0. Okay, b is already greater than 0. So product of things that are greater than 0 is still greater than 0. Okay, so maybe I write here. So c greater than, so c not equal 0 implies that c squared is greater than 0. Implies that c squared b greater than 0 because b is also greater than 0. Okay, this is the first thing I think we'll do in FA1. Then what else we need to check? The c, the denominator is non-zero. So does this look non-zero? Does this look non-zero?
Square root.
Must be non-zero. Why?
If it's still using non-zero, I cannot be.
If it is 0, what happens?
If it's still using non-zero, it's a minus square root of b.
Why?
Why?
Sorry. Why? Okay. So well, I mean, like, suppose, okay, if it is, you want to show that it's not 0, right? You can use contradiction, right? Like what I did last time. So suppose a squared minus b equals 0. This will tell you that b is equals to a squared. Then this will contradict this condition that b is not. So that's why this condition comes in, Yeah, so for mathematics, right, every condition we put here is necessary. You will have to use the summation. If it's not necessary, we will remove it from the thing. So that's why we say that b is not necessary. Make sense? Okay. Contradiction. B is not. Okay, any questions so far? Maybe up to this stage, you will feel that logic is pretty important in this class area because if you see the assignment, right, there are questions that related to making inference and making conclusion, and not just simulation. Okay, but not too abstract. Okay. Right. So any question for this one before you try the next one? Okay. If yeah. Okay. So you know how to start with this? The sum of a rational number with a quadratic irrational. So you take something p over q plus something in this form. Then you want to write it in this form. Extend the thing inside the square root and extend the By the way, previously, did you see that why C square B is not study because B is not. So there are three things to check. What's your last form? PC plus AQ plus square root Q squared B over CQ QC. Okay. Sure. Good. Okay. So similarly, you check three things, right? Okay. So, well, first thing you could check is Q square B is not perfect square again. Similar reason, because B is not. Okay, so you can use contrapositive to see that if B is a perfect square, and the whole thing is a square of QB. Second, what do you need to care about? Q square B is greater than 0. Again, similar idea here, because you are multiply a positive number with a Q square is positive again. So again, it's positive. Okay. So I'll write here because Q square and B, both of them is greater than 0. Third thing, what's the third thing? Third thing is QC is not 0. Okay, why QC is not 0 here? Because Q and C is already not 0. Okay, but if we change the number system, maybe this is not already. Okay. If you work in a different number system, like we already see it, right? Like congruence, modular congruence. There's two things that non-zero could multiply to 0. Okay, for example, in mod x, right, you can take 2 times 4, becomes 0, but 2 is non-zero, 4 is not. Yeah. Surprisingly, you guys put group theory into the solution, but unfortunately, you won't get marks because this is not all about group theory. So make sure you learn the solution within the scope of this class. Otherwise, if you use scope of scope, then it means that you don't understand what we learned in this class. Okay. Even if it is correct, I cannot give you marks. Okay, because you are not learning stuff from this class. If you learn more, that's very good for you. Okay? But then we have to assess you in this course. If you really like group theory, please come to MA. I'll let you do group theory. Okay. Yeah. Yeah. So please don't put advanced solution into your Send. Okay. Um. All right. How about let's do some. Oh, okay. Before that. Okay. So for this theorem, right, proposition, what can you see is quadratic irrational kind of comprises a big family of numbers. Okay. For example, if you have a quadratic irrational, you take one over the reciprocal of it, it's still a quadratic irrational, meaning you take the inverse and reciprocal. Or you can sum it with any rational number, still can solve a quadratic equation. Okay, with integer coefficient. Okay, so this already include a lot of number, a lot of letter numbers. Right? Does it make sense? Okay, so this is quite a large family already. Okay, how about try to work this out? See what's the number you get. See if you know how to set your x properly. Maybe I give you 3 minutes and work this out. Okay, everyone got it? Same? Same? Okay. Anyone got other questions for this one? Okay. How about we try a different pattern? Maybe we can quickly check. There's this one. Maybe this one is more tedious a bit. Let's try this together. Huh? What do you mean 8?
It's 8 and sub 3.
8 and sub 3? You mean, yeah. So first term, you should get 3 over 2 plus minus. What was this term you were trying to say? Huh?
3.
3? 3 sub 8 over nothing.
What?
24?
No, upside you.
Ah,
For them.
so what do you get for second term? 3?
Yeah, surely.
Just 3? So nice. Okay, let me see.
Square root 3.
Huh?
Also get that last one and 2 become 8 square root 3.
X squared times 3, is it? Like that?
Yes.
Yeah. Good. Okay, so you get sub 3.
One more 3.
One more 3?
Oh.
Why is there one more 3? Okay. Yeah, sure. Okay. So, well, since x is positive, okay, x to be. But obviously, sometimes you need to be careful. It's not that always you have minus sign, this thing has to be positive. Right. So for this, I think if in this case, I just figured out the term that's repeating. Okay. So which is this term here? So well, we need to kind of expand this. Okay. Okay. 4 minus 3, which is this is 12. So I get 13. So ugly, this number. Let's see if this is the right thing. Huh? People play? get something like this. 36 minus 4 times 3 over 30. Is this right answer? A bit too much. My final solution is 29. Did I do something wrong? Huh? You get 29? You get 29? Did I do something wrong? I don't know. I look at the previous solution is 29 plus 4 square root 3 over 13. Any other, I mean, like, yeah, where's the mistake? Hmm?
X again.
Or the x I get is different. So something wrong with my quadratic equation or not? Do you get the same quadratic? Root is different. Same final answer or same x? Same x. X is correct, is it? Okay. If x is correct, then maybe substitution is wrong. Is the substitution wrong? Okay. I think, yeah. I think I forget to take the reciprocal, is it? Yeah, I think I forget to take the reciprocal. Correct or not? Because the shape is like this. Yeah, forget a reciprocal. Okay, so pretty important. Yeah, so this reciprocal is very important here. Okay. So okay. No wonder this thing like look very weird. Okay. So let's do whole thing again. Not really again, right? Let me see. Let me see. So can we like improvise a bit? Okay, I think we could. So let's improvise a bit. Because the shape is similar, so let's just improvise a bit. Okay. Okay, let's improvise a bit. So 1 over 1 plus. Okay, so here become 3, here become 3, here become 3. Okay, so I put this back here. Okay, like that. Okay, and then so we evaluate this thing here. It's 1 plus. Okay, so I think we could reuse this possibly. Okay, but with a different calculation. So here. Huh? What? Okay, so you're talking to yourself. 9 over 4 minus 3, like that. Okay. There's another reciprocal to take. Crazy. Okay. So, okay, I guess we can remove all these first. Okay, so so the top here, we should get 3/12. So you get negative 3 over 4, is it? Yeah. Okay. So then, well, we can push the minus 4 to the top first, is it? Okay. And then we could divide this by 3. So I'll get half minus square root 3 over 3. Like that. Is it okay? And this? Okay, let's continue. 1. So there we get 3 over 2 minus square root 3 over 3. Is it correct? For those who are calculated before, to prevent I restart again. Correct? Huh? minus 4会撒上去，我想一下，删错东西啊，是不是？应该要先删上去。 Okay. Sorry. 算了，我们一个一个来。Yeah. So here is minus 4 over 3. Here is 3 over 2 times minus 4 over 3. And then here is minus square root 3 times minus 4 over 3. Yeah. So 应该要把减3弄上去 instead of 那个。So, okay. Let's move more stuff. I want to move negative 6 up because I want to make the bottom without denominator. 老师不会出这个问题 ？OK， 多点保佑。Okay, this one 16, right? Sorry, 12. And then this one is minus 8. 对吗？谢谢。感觉回到高中了。Okay, so in that case, 如果我要 push negative 6 out, then this one become 6, right? 哎，对吗？对 ，correct? Or actually negative 6. Yeah. 对哦。Here multiply by that's 2, right? Then here multiply by plus, 对吗？Okay, so no denominator here. We get, yeah, better now. So here is 6 minus x square root 3, right? Is it? Okay. Then we can multiply by this conjugate again. 啊？什么？有算错吗？有算错吗？帮我 check 一下，不然等下又要重算啊。Damn，反正你在家也是这样一直算，是不是？Okay, it's okay. So 我们也是一样的。Okay, so here we get 64 times 3, right? What is it? 192. Oh, again that magic number, huh? Okay, 192. Okay, hope that we can get what we want. What's this? Negative what? Negative 685 156. Okay, can we simplify it? Can. Divide by 4. So 4, 9, 4, 12, and then 4, 4, 3, and then 4, 4, 9. Okay. Yeah, that's it. Okay, for now, that's it. Sorry? Oh, divide by 3 again. Okay, very good, very good. Yeah, magic number 13 come already. Okay, 4, 9. Okay, good. Very good. So 3. So 3, where's my 3? 3 plus 4 square root 3 over 13. Okay, so here, so we get, minus 13, Okay, so push it up, become plus. Okay, good. So finally, we got our 29 plus 4 square root 3 over 13. Okay, good. Yeah. Good. Okay. So far, okay? So far, so good. Okay. So quite tedious, huh? Maybe you can try this also. 2, 3, 2. As a homework. Homework now. Homework. Okay. Yeah. 哎，几点了？哦，I think we should 去厕所。差不多要 break okay. Okay. Right. Let me see. Should we go to the next one? I mean, let's take a break. Okay, let's take a break. Let's break until 10:39. 这明显没有在太早了，没有嘞，换人来。 很 enjoy 上课。
课都不要来。
I missed last session. I couldn't take
Okay.
my
Okay.
assignment.
Okay.
So here, this is not 5 to the power of -2. That's
With the
that's 5 to the power of 2.
Right. Okay, good. Yes. Okay, sure.
You said not an integer.
Sure. How many marks I do?
One.
One mark. Okay, good. Can you like screenshot this and then send me on
On Teams.
Yeah. So that I can go back. Okay, check. Yes.
有啊，怎么样？
我想问比如说这个这道题，就是我看你写的过程很多
啊，
然后我就想先这个
明白
然后我就可以直接就3
明白。
就是我考试上写的可以，还是必须要按照你那种比较复杂的方式。
是，它其实是一样的东西。通常我们这一步会接一步，就是除掉2672，除掉231，then 这个316122就会出。
就是像这种的，这是
也
必须要写出来的，
比较好的，因为怕有些老师以为你不知道。
就是那个当时期末批评老师，
对，
这不可以。
对，没错。
好。那我以后就是
你可以写这个，写这个，写这个，直接写那个不需要，直接写这个应该可以了。这样就知道你是用那个这个
明白。
就算他不接我，我年底了。
还有一个这个地方，我觉得就是把 A0写成 T0，就是比较符合这个规律。
对 ，anyway 对。
然后为什么这个地方要加1呢？这是一个规定是吗？
对，没有错。这两个其实这两个是你需要这两个才可以开始这个，不能只稍微一个去这个，除非像我讲的，你要有一个减一。如果你没有减一的话，这两个就要从这两个开始，或者用我的方法，就是用减一跟0开始，看你怎么去看这个风格，因为这风格肯定需要你前两个被定义的，对不对？说这个关于这个怎么来的，就是你怎么展开的这一块。
那刚刚老师说那个
减一
和0，
对，减一的意思就是说，如果我 define 了P 减一和 Q 减一是什么，我就可以从 P 减一跟 T0得到 T。
那个我们学的是从0
对，没错，但是也可以从减一开始的，
就是那个就是这两个必须要先出来。
对，没有错。
我懂了。
我是会聊聊的。
然后一会儿我11点到1点开了这个，可能一会儿我就从这个
我自己来，
因为咱们这课是1点半下课嘛，所以
OK。然后你1点半走，
我就是另外一个课，我已经就是只要是没事了，我就马上回来。
那个也没有点数的。
应该30年。那我签到了，
不用签到，我没有签到。好，因为大家
然后还有一个就是我们有第4个没有了，
就是那个你自己做的最好的，会发。
所以说就是那算分了，就是那大就是跟上过了，然后咱们下周2就考试了。
对，
那就是现在就是那我们那个就是那个最后一章，就是复习时间很短，感觉挺吃力
所以我们不会出特别难，会比较直接的题目。所以说 assignment 4很重要，大概就围绕着那。
然后就是在网络上没有答案的交流， 就那个后面会后面会给我做一些，然后发现一些
你也可以发我，然后我们就会各位讨论，或者你也可以用 AI 检查。好的，好的，可以。Okay, maybe later I'll teach you a skill. Use your AI to check your solution. Yeah, I can teach you a skill. So you don't need to ask the question. But then if you have, I think if you have any confusion, yeah, you have any confusion, right? You can discuss with them. Because nowadays, I also use AI to like help me to work out the preliminary solution. Then I can adjust based on them. So the point here is not like you rely on AI too much, but then the AI is a very good starting point for you. Okay, it's not that anything AI tell you has to be true, but then AI did a very good thing is the searching skill is very good. So it saves your time to search all the paper or make summaries or stuff like that. But then obviously you can question it. I always question my AI one. Is it true? Then he will say, sorry, it's false. so you have to question it. Okay, you have to keep questioning it. Then you'll get better. Sometimes what he says is wrong. So you need to be aware. Is everyone back here? Maybe rest a bit. 评分，讲评分。
就讲说评分，然后你评高分这样子写。
哦，你给他什么 proof 这样种？哦，他怎样评分？
有跟你想要这样子可以吗？
哦，OK，可以。
教回我，要回复的，他回复的方式好像我讲不一样，讲的康复啊，认真，我现在讲不通。他们这个跟电话是不是怎么是跟电动是什么神经压过吗？我跟你压到跳了。我也是这样子觉得。对。打几块，然后也不错。那走这个就笑。
拜拜。我换位置。
哦，我不敢人家走。
没有啊，我哪里知道？他拿着 bag，我以为他走。Okay, if everyone here, maybe we can start a little bit earlier. We can finish earlier also. So for example, just now, right? I calculate. I don't know my answer is correct or wrong. Okay, so I screenshot this. Okay, so I go Gemini. Do you guys get free Gemini last year? Last year they gave a free Gemini Pro version. Okay, so I put my photos. Everything you can ask Gemini. Everything you can ask Gemini. Yeah. Anything you can ask Gemini. So send this. You see, I think I want you to observe how they calculate. I mean, what's the thought process? Okay, this thought process is very important. It's like how you decide, how you do this. You should do the same thing. Okay, analyze what is it, what's the level effect, then calculate some finding the relation. Yeah, this is how you process the question. Okay, so see correct or not? See if the Gemini gives us the same solution. Okay, see? Okay, so if you don't believe, let's say I say, okay, oh, this solution is different from mine. Then you go back and check the set one by one. Is it correct? Usually, if it is the same, you cannot recognize it's true or false. But if it's different, then you will definitely go and find out the difference, whether you are correct or it's different. Yeah, sometimes I always find mistake from Gemini. I said this set is wrong. Then Gemini will say, oh, sorry, this set. Yeah, very good. Yeah, okay. I think it's better than like, so Gemini can respond to you. Okay. Yeah, very good calculator. And nowadays, actually also find Gemini doing good proving stuff. Yeah, proof stuff proof question is also very good. Yeah, I can do advanced stuff also, like advanced topics. Okay, good. Yeah, so for example, right, in your assignment, right, you give me all sort of primitive root of. Should I go and calculate all of them? You give like very large number. Okay, you do one is but then I mark so many people and we give different solution. How I check. So first of all, I ask Gemini to check first. If it's okay, roughly okay, then it's okay. Yeah, like that. You guys give a lot of like primitive root. I mean the maximum power, right? For 3072. Right. Yeah. Surprisingly, the answer I told you is correct. It's 5, right? But then in the solution, the answer is quite large, actually. They combine 2 congruents, but actually 5 already work because 5 will be the what will be primitive root for the x, the 3 cube, and then for 2 to the cube, 5 also will attain the maximum of the so 5 will work. But then the solution will use 2 because 2 is always, not always, for most of the case, it is a primitive root. But then I think some of you use very special answer also, like 570. Because you use 3, I guess. Yeah. I mean, yeah. You combine with 3, I mean, instead of 2. Okay, so this is it. Yeah, so I think you just input the set of tutorial questions that I gave. Then you check whether it's correct or not based on what you're doing. If you have conflict, you don't know, then you bring it to the class, then we can discuss. Okay, right. How about this? Okay, so for this one, what would you do? Okay, if I give you this question here. So find simple continuous fraction expansion for 1 plus square root 17 over 2, then find a simple continuous fraction for 11 plus square root 17 over 2. So maybe you just tell me what to do first and then see if you want to do it. What do you do? Huh? What do you do? Sorry?
Compare with the formula.
Compare with which formula?
Minus b.
Minus b.
B squared minus squared. Okay.
Ah. Why is that useful? Okay, yeah, sure. So this is quadratic irrational. Then so okay. Let me write down what you say. So you mean you let x to be this thing here. Okay, so then it will satisfy some ax squared plus bx plus c, is it? Then you can read it, I mean, write in some form like some, I mean, don't know what is it, but then like something like that. But then you still can't figure out the whole x, right? What we want now is like the continuous fraction. What do you mean?
I mean something like
You know the pattern is repeating, but you don't know what's the pattern. Is it possible? It's not possible, right? Is it possible?
n+1 over n+1.
Oh, I think it's possible. I think it's possible. Well, okay, let's try what you say. Let's try what you say. Okay. Okay, let's try what you say. See if it works or not. Okay. Well, okay, so how do you work out the quadratic equation here? How do you work that out? So do you just compare with the formula? Is it that easy? 试一下，试一下。Okay, let's try. So then minus b will be 1, and then 4ac will be 17, and then 2a will be 2, like that. So b is -1, a 1, 3. Sorry, b squared. Oh yeah, sure. Thank you very much. No wonder I see why there's no b at other place. Okay, b squared minus 4ac. Okay, thank you. So in this case here, we'll get 1 squared 4. 啊，这么快 ？c 等于 -10，-4 -4。Okay. So in this case here, our quadratic equation is so x of ax, huh? So it's x squared minus x minus 4 equals 0, like that. Okay. Then you say that I just play around with this, right? Huh? X squared will be equals to x plus 4. Then x will be equals to 1 plus 4 over x. And then we turn it around, is it? So 1 over x over 4. Then
4 over x. Make it 1 plus 4 over x.
how to do that? How to do that? Huh?
X if I had a expansion to 1 plus 4 over something.
How? Is it possible by engineer?
It can be like this.
But
something like this. I'm not sure. That's my idea.
Your idea?
Just
No, right? Because this will have always be 1. Right? Should always be. So maybe let me try something. So 17 should be in between 16 and what's the next square? 25. So square root 17 is in between 5 and 4. And then square root 17 plus 1 over 2 is in between 3 and 5 over 2, which is greater than 2. Is this helpful? Huh? So this the flow. So what I wanted to say is this implies that the flow of x should be 2. Huh? So the flow of this is 2.
你再说呢？那个确定的 x 是2点几嘛？然后那左边的那个 x 就应该等于2加多少？左边加4加。对的，下面以后也是2加 x。
You mean you want to prove the
没有，就是把那个乘加乘法就多减一倍加一减，加一减，然后上来对的，2加4加。
Okay, so instead we pull the 1 out, we make the extra one, is it? So you mean we make the extra one? So you mean like this? 试一下。Then you're gonna combine this, is it? So it become minus 4x plus. Okay, so 4x minus, sorry. So x minus 4 over x, like that. Correct. 变成加好看一点。对，应该要变成加，因为我们的那个是加。OK， 给它倒下来，给它倒下来。Taking reciprocal, you mean, right? 然后
这是还是哦
啊，
这是还是
什么意思哦？还可以再做吗？
为什么还在补充我要让它第二个出来吗？
Oh, you mean find the flow of this thing again? You mean find the flow of this? Wow, getting more complicated. You can do that. I think you can do that. You can do that. Yeah, you can continue doing that. Otherwise, because you know the flow of this, right? Then you can apply whatever we did like 1 hour ago. Right, I told you this formula here. I mean, it's similar idea, right? But then you will specify in terms of x just now. Then if you just go straight and compute it, it's fine. Yeah, go straight and do this. Does that make sense? Yeah, so you just do the formula that I told you at the start. Okay. Otherwise, if you continue in what we did just now, you will be doing in the form of x. But I think it's the same, I guess. It's the same, should be the same. Okay. Maybe I can tell you the answer. So if you apply the formula that we started just now, I can actually tell you the solution first. So this thing here, actually you will get 2. Okay, we are correct with the first one, and then the rest is repeating 1, 1, 3. So if we take the flow just now, I guess you will find 1. Okay, or x over 4, for instance. Okay. And let's say we know this, right? I think the more important part of this question is, can you get the second one? Okay, because we said then, right? So meaning we should use this answer to get the second. Do you see any relation between the first? Yeah, 5 plus 5. Okay, so very good. Okay, so actually this is just 5 plus 1 plus square root 17 over 2. Okay, remember what did we say just now? You have a quadratic irrational. You plus a rational number, then it is still a quadratic irrational. So you can see that it's a quadratic irrational. Just means, but then how do you like combine the simple continuous fraction? Huh? What do you mean? It's a different number, right? So different, right? But then what to do there? 5 here is what? It's an integer. So you just add the 5 to the first of them. Okay, so meaning, so if you meaning if you take 5 plus this bracket here, okay, you are literally adding 5 to the first spot. That's it. Okay, so the new continuous fraction is 7, and then repeating 1, 1, 3. Okay, no? Yeah. Yeah. Does this make sense to you? Does it make sense? Okay, because you need to remember what this shape is. This shape is basically 2 plus some fraction. Okay, so you're adding integer, right? So where you adding? You're adding to the 2, right? Yeah, so you're adding 5 to. Okay, so you're adding 5 to 2. Any question? Does it make sense?
反正一个4嘛，一个 x 零 x 是啊，乘以4嘛。我就是把那个前面
哪一个前面？
是213，
213对不对 ？OK， 这个怎么得到？So use this formula. 知道这个 formula 怎么用？因为嘛，没有，不用计算机，不用计算机。So you just use this. Do you know how to find this? Square root 2 and then work out this thing here. You know? So first of all, you find the floor of your alpha 0. And then you take this formula. And then work out what is the next term, what is the next term, what is the next term. 可以啊，可以，也可以，但是你也会进入到这个方法，你也会进入到这个方法一样的。你看啊，你看啊，看清楚啊。来 ，what did we do here? We also look at the we also like resort to finding the floor first. Yeah， 一样的，只是说这个 x 的方法会比较就是你要小心一点，它不是这么直接，要小心。你看啊 ，you only have one here. Usually we want the whole integer part. So you need to realize first your integer part for x. So actually it's 2. Otherwise, this one here, this 4/3 here, right, doesn't fall into the range that we consider. Is it? Can I say like that? Yes. So this term here is not in between 0 and 1. Remember, what we did was we have to make this term in between 0 and 1, only then we can swap and then find the integer part, swap, integer part, swap, integer part, taking reciprocal integer part. Yeah, so you need to make sure that this part here is in between 0 and 1 first. Yeah. Okay. Yeah. So we need to pull out the extra 1 first. Only then this thing is in between 0 and 1. Only then, yeah, you can continue your making floor and it's the same example that you have more terms to look at. I mean, need to be careful. Because in this formula here, right, once you take the floor, the difference between your original term and your floor is already automatically in between 0 and 1. Which part is in between 0 and 1? So this part here is automatically in between 0 and 1. So you can straight away take reciprocal. Just now, it's not yet in between 0 and 1. Because we show that this 4/3 here, right, is something less than 3. You see? Something less than 3. Okay, so if you take 4 divided by 3, it's not in between 0 and 1. So you need to take away something else first. Only then this thing here, the whole thing here is in between 0 and 1. Okay, then you take reciprocal, then you pull out the integer part. Then you need to make sure that that thing is in between 0 and 1, and you take reciprocal. Then, yeah. So this is a whole similar idea between decimal expansion and continuous fraction. Okay, so that's why I make this comparison with you. Okay, before you take integer part, make sure that you lie in between 0 and 1 first. Okay, so first you take difference between floor, lie between 0 and 1, and shift 1 to the decimal. The other one, you take also take difference between floor and 1 over the things that's in between. Okay. The whole idea is keep making your term, the terms that's left over in between 0 and either you take a reciprocal, make it greater than 1, or you multiply by 10, make it greater than 1. The whole idea is the same. Okay, so far, still got question or not? Okay, so don't be scared by this weird cert here. So the formula is still the same. Formula is still the same. So don't be scared by this cert here. Okay, because the formula I gave you, the alpha, right, is work for any number. Okay, any number, as long as you can work out the floor. As long as you can work out the floor, then it works for any number. Okay. Any question? Feel free to question. Okay, so then this will left as the exercise as well. Okay, let's see. What's an important thing we should do next? Okay, so we have a theorem here. Okay, so we also provide you a formula to find AK if your alpha is in this form. You don't need to go to the first calculation. Okay, we will use the first calculation to derive this formula. So what does it mean? So let's say you are quadratic irrational numbers. Okay, so how to find this A0, A1, A2? Okay, so what you do here is, again, these numbers here should be flow of something. Okay? So I will tell you what's alpha k here. So this alpha k here also in each term here will looks like a quadratic equation. It's pk plus square root d over qk here, but it's defined inductively like this. So let's look at it. So a bit powerful here. Maybe I write here. Well, let me see. So I guess the better way to present this is I write define AK to be this, where the rest is like that. Okay, so maybe I write in this part here. So this will tell you the sequence. Okay. So we will get all the A I, okay, as a flow of some alpha I, and then this alpha I will be defined as some quadratic irrational. And then this quadratic irrational will be defined recursively. Okay, so what can you see here? So you see that the PK, right, actually defined using the previous denominator entity. Okay, but then this denominator is multiplied with your AK, okay, the previous AK. And then take away PK. And then QK plus 1 is a bit weird. Is a D, so something inside the term minus T squared of PK plus 1. So meaning to get QK plus 1, you have to first calculate PK. Okay, and then obviously depend on the previous QK. Like that. And if you are curious, right, you just extend the first few terms, then you will see this formula. Actually. So you can see that the square disappear because your P already taking square. So that's why you can imagine that I'm taking square on both sides. You want to see the first few terms? Why it appears like this? Oh, you okay? Let's see. Maybe I can show you the first few terms. Okay, then I think this will make more sense on the calculation that Swanfen suggested just now. Okay, so what should we do first? Okay, maybe we just work out what is A0. So A0 is, so let's write down. A0 is the flow of alpha 0. Okay, so alpha 0 is what? So basically, alpha 0 is just P0 plus square root D over Q0. This makes sense or not? I just think my computer does not look at it. So this is the part. Good. How about the next term? So if we use this formula, now we are kind of a back engineer. So back engineer meaning I give you the formula. See you work out why I gave you this formula. So you should imagine before this formula, right? They are trying to work out this formula. So they use definition to work it out. But we are kind of doing back engineer. So we try to write down what they say and then see if it makes sense or not. Okay. So A1 is alpha 1. Okay. Flow of alpha 1. So which is P1 plus square root D over QK. That's right, Q1. Okay. Well, so how do you define P1? Well, P1 is A1 times Q1 minus P1. Sorry, it's Q0, right? So it's the previous one. A is also A0. Sorry about that. Okay. Then QK plus 1, what is it? So it's a D minus P square 1, right? Okay, P square 1 is something above, right? Which is When I think I'm missing square root d here. Okay, let me put a bracket here so that I know what I'm doing. Okay, maybe I write what is P1 for you so that we are at the same page. So here is P1 square. So meaning I take this whole thing square. Maybe it looks very ugly at first. Later we're going to expand it and then see what's really happening. Okay, so A1 is taking a floor of this guy. Everyone agree? Agree? Okay, so let's see if this thing makes sense here. If this thing makes sense. Shall we? Shall we expand this? Okay, not necessarily expanding this. So what did you see here? This whole thing looks very suspicious, right? You can cancel it as a conjugate. Right? I can, right? Okay, so if I cancel it, what do I left with? What's the conjugate I can cancel here? Okay, maybe I don't write it in this form, maybe it's easier. So P1 plus square root D over D minus P1 square. I think in this form, you can see it clearer. Okay, so what's the conjugate here? What's the conjugate here? Well, I write this as square root D minus P1 square. Sorry, no. Times square root D plus P1. Make sense? Is it okay? Okay, good. Good. Okay. But then if I cancel out this term here, what do I get? I just get Q0 over square root D minus P1. Like that. Okay. Well, this is not quite we like, is it? See, E1. What's Q0 actually? Oh, Q0 is just denominator. What's P1? P1 is something looking like that. Okay, good. So what if I put P1 back? A0, Q0. A0, Q0, and then P0. Wait, no, sorry. This is taking away A0, Q0 plus P0. Okay, but what is this here? Okay, what's this? Huh? Well, this is just 1 over 1 over what? P0 plus square root D over Q0 minus A. Can you see it? Is this A? A0, sorry. This is A0. Can you see this? Are you recognizing this? I recognize this. Is it A0 or alpha 0? Huh? A0, yeah. Okay, A0. Are you recognizing this? Can you recognize this or not? Can you recognize this? Okay, look at the formula again. Look at this formula again. So that's why I remind you about this formula. What is this? 1 over the alpha k. The alpha k is the thing that is take away the floor. Okay, so this is this guy here. 1 over the original term. The way the so by induction, then we will keep doing that. Does it make sense? So that's why there's a lot of this weird term coming up, exactly because of this kind of cancellation, the conjugate calculation. Okay, so far. Okay, yeah. But to prove this, you need induction. Okay, I just give you an idea why it works. Okay, in that case, shall we apply the formula to this? Let's apply the formula to this. Okay, instead of using the way that we started at first one, find the difference. Try and use this formula to get the solution. Just want to check if is your alpha one looks like this.
不满足条件，
什么条件的啊？这个整除的条件不满足啊？ 这么夸张？Let me check 啊，一加
哦，
没有满足吗？Okay, so there's a condition here. Point out. Forget to mention to you. Square Q not should divide D minus 1 square. Doesn't divide, right? Ui. Wait, let me see. Wait, interesting. I think this condition shouldn't divide. It's not divide, right? Divide. Oh, should divide because this term should be a integer. Why then this form? Bad example. Huh? Bad example. Why this example appears here? Okay. I didn't verify it because I thought it's immediate, but then it's not. Huh? How come? In that case, maybe you can change to 2.
Yeah, 2 will work.
We can make it 2. 2 will work, right? Yeah, I didn't check. Wait, let me see. Let me see what the previous person do. I thought it's obvious, so I didn't really want to check it. Let's see what people do. Maybe they try different stuff or what? Turns out as I think it's a bad example, so I'll remove already. No wonder I cannot find it. Okay, let's see. Okay. In that case, how about we change question? Make it 2 so that it is divisible. Yeah, make it 2. Okay, so let's make it 2. Let's make it 2. Yeah, then we try and compute again. See if it works or not. Yeah, so let's make it 2. 2 should be divisible already, right? 2 divides 11 square minus 1. You know why this condition comes in here? Otherwise, why just give Okay, so let's do this. Let's say if we change it to 2. Yeah, those look a bit nicer now. Okay, here is 2, here is 3. So in this case here, this one become 2. Okay, let's continue. So Q0 become 2. Okay, good. Q0 become 2. 2 here, here become 2. 2. So 2 minus 1 is 1. And then 2 minus 1 square is 1. So here is 10. So here is 10 over 2. Okay. So here is 2 over 10. Here's 2 over 10. Yeah. So it's 2 plus 2 squared 11 over 10. Like that. Okay. So is it easy to see this? So 2 plus 2 squared 11. What is this? So this should be in between. Okay. Should we? Maybe. Okay. Just do it step by step. So 2 squared 11 should be in between 8 and 6. Right. And then this implies that 2 plus 2 squared 11 will be between 10 and 8. And then if you divide by 10, so this one is something greater than 0. And then the other side should be something less than 1. So meaning this integer here is 0. Okay. Okay. And then we should continue, right? Should we continue? Do you want to continue? Huh? You want to continue? Or we should go to Gemini? I'm a bit lazy. Okay, you can continue. Let me check Gemini. Well, let's see. Let's see if Gemini can recognize this correction. See how Gemini read this picture.我要搞疯那个 Gemini. Okay, let's try. Let's see if the Gemini recognize the correct version or corrected version of the old version. Yeah, see, Gemini process. This is what you need to do when you analyze question. And I like to expand this part. Last time can expand this part. They will list down everything. Wow, Gemini did very well. And even read out the change question. So first one is 2, right? See the second one, is it 0? 6. This is bad. Did we do something wrong? 1 plus square root 11. Yeah, let's check our solution. 1 plus square root, correct? So A0 correct already. How about the next term? So this Gemini will be using the first method we learned, right? The first method we calculated. X naught minus the 4 the small again. But then the floor they found is 6. But what I do is 0. So something wrong here, is it? Formula wrong or not? E1 plus square root 11, correct? And then P1 is A0, A0 is 2. A0 is 2, yeah, correct. Something wrong. Did you see what's wrong? So A0 is 2, right? But Q0 is also 2. I put a 1 here. Correct or not? Did you see? So this is 2, right? This is also 2. Okay, so this part should be 2. Okay, let's try. Let's correct again. So this part is 2. And then this means this part is 2. Okay, so let's check our solution. 4 minus 1 is 3. So this part is 3. So that part, 3, 3, 9, no? 11 minus 9 is 3. So here is 3. 11 minus 9, right? So it's 3. 2. 4 minus 1 is 3, right? 3 squared is 9. 2 over 2 is 1. So it's just 3 plus square root 11, no? 3 plus square root 11. But what is 3 plus square root 11? This implies that 3 plus square root 11 is in between 6 and 7. So it's 6. Okay, Gemini is correct. Okay, good. Okay. Yes. 什么意思？就是你看到之前看到之前那个，乘3 OK。
现在剩下都乘3就满足条件。
上下都乘3就满足条件。Let me think. So 3 plus 上下都乘3 Oh, I think I get what you say. Wait, let me think. 9 divide 9 times 11, is it? Like that? Let me see. So 9 is 9 dividing D. So D minus P is not squared. So 1 squared. So you're saying this is true? 对吧？不对。P043，看一下 P043 OK, thank you. So P043 3 square like that. Like that? Cool. Very good. 对吗？What? 9 times 10, right? Good. Yeah. So you can also work out, you mean, right? But then, yeah, definitely. Yeah. But then, what happens if you just use this to compute? I mean, if you just, what happens if we continue just now? Like, just do this. What happens? Did you already compute, like, what's the next term? What did you see just now? Or you haven't compute, you just say that it maybe doesn't work. Because what I could anticipate is definitely this term is not an integer. But then I'm not sure, can you just, like what you did, maybe you apply top and bottom, then you can make it an integer top and bottom. Yeah, it could be in that case, but I haven't tried it. You get what I said? Yeah. But then, is everyone okay with this first before we go to the now what your friend said just now? If everyone getting this, the formula, calculating using the formula versus the original formula. Everyone getting this? Is it okay? So they both compute to the same thing. Okay? It's just that we already process this part here. Process this part into formula. Does that make sense? Okay, so if you study until this week, right, you can see that a lot of formula is depending on the previous terms. Because this is exactly how we set up our calculation. We use the previous term and then we reciprocal and then we compare. Because it's depending on what's due. Yeah. Okay. So coming back to this, maybe we can make it an exercise like what about the original one? Yeah. What about the original? Okay. Yeah. So you can try and use this versus like what we did just now, right? Like what your friend suggests. Like this. Wait. So here become a 9. Yeah. So try and apply formula on this and then formula on this. Let's see what. Does it make sense or not if you apply formula to this? Okay. So apply formula here. So and see if it makes sense. It doesn't make sense is because the denominator part, the Q0 part, QK plus 1 part will be non-integer. Because you can see that I think it's not just P0, Q0 have to be integer. I guess all of these will be integer, okay, based on this. I suspect. Even if it's not integer, right? Maybe you can, like what you say, multiply by denominator, then in that case, would it always be a perfect in the form of perfect square? Yeah, there's a lot of things that you need to consider. Because we don't look at this proof, so it's quite, how to say, quite unclear that why we set it like this. Yeah, I just show you a few terms here. Okay, it's not enough. Okay, so we need to prove for all k actually. Yeah, so in that case, maybe we can try this. Okay, I will try this as well. Yeah, we'll see in the notes how it goes. Yeah, so far any question? So far any question? Yeah, so please be reminded that this divisibility condition here is to make sure your QK is an integer. Okay. At least QK plus 1, Q1. Right. Okay. Yeah. Sure. So maybe let me see how many more. Okay, maybe just 2 more. Okay, before we break. So Lagrange theorem says that the infinite singles continuous fraction of an irrational number is periodic if and only if the number is already irrational. So basically, you have a few categorization of already irrational numbers, or if and only if this number can be written as a plus b square root b over c. like that. Okay, C is non-zero, and then B greater than 0. And then what else? B is not a perfect square. Yeah. Okay. So if you see an infinite simple continuous fraction, simple meaning the ai are integers, okay, and then it's periodic, then this number is a quadratic irrational. Is everyone fine with the definition of periodic? I think I haven't really defined it for you, right? So although I give you few examples on periodics, so technically when we say periodic, right, we don't really care about the finitely many first term, finitely many first few terms. We just care about the n terms. As long as your n term is periodic, in periodic form, is called periodic infinite simple continuous fraction. Okay. Yeah. So for examples, there's a few examples in your notes. These are all periodic. See? Okay. First few terms is not in periodic, is fine, but as long as the rest is in period. Okay, like this. Okay. Make sense? Okay. Okay. So this is the Lagrange theorem. And then the other thing is if even if the first few terms are all the terms are in period, then we'll say it's purely period. Purely. So if a simple continuous fraction of a quadratic irrational is purely periodic, if and only if actually this term outlier have to be greater than 1, and then the conjugate will lie between minus 1. Okay, I mean this guy will be purely periodic. Next one is a very special theorem here. This theorem is very nice. So it says that if D is not a perfect square, then the square root D will be in this kind of form. So observe that the last term in the period is 2 times the integer part. Actually, more than that. If you look at the textbook, actually it's more than that. There's a very nice symmetry here. I don't know why, but there's a nice symmetry here. So let me show you. What happened in between was this. This part here. Yeah. This part here. Okay. So actually, what's in between here is you have to like palindromic tracing. You know what is palindromic? You read from the front, you read from the back, it's the same. Okay, so it's like A1, A2, A3, AN, and AN minus 1, AN minus 2. So what happens is not just the last one is A0. Actually, what's in between A0 and 2A0, right? Is this palindromic thing. Okay, I give you examples. Maybe it will be clearer. So this is the example. You see the palindromic? So for square root specifically, you have 1, 3, 1. And then 8 is 2 times 4. And then the square root of the 1 is 1, 1, 3, 5, 3, 1, 1. Palindromic. So the read from the front, read from the back is the same. And then the last one is 10, and then 5 is 5 times 2. Very weird. Very weird. Okay. So to calculate all these is just the first hour that I told you use that. Okay, if you cannot remember the formula, never mind. Just use the original method. Okay, use the 1 over alpha 0 minus 6. Just use that. And then find the flow. Because all the formula is just derived from that thing. Okay. No need to memorize whatever formula. It's not torturing you. You just use the first original method. It's already good enough for me. Why the formula is important? You know why? Because it's recursive. So if you tell a computer, it's easy to do. Yeah, instead of you taking floor, right? You do take floor, but yeah. Anyway, sometimes it's better for computer. That's what I wanted to say. Okay, any question? Yeah, basically this is it, okay, for this part here. Okay, so we have learned like finite continuous fraction, infinite continuous fraction, and then infinite continuous fraction that's periodic. That's it for this part. 6.1, 6.2, 6.3. Then got 6.4. So meaning, am I missing one of the subsection? What's the other subsection here? Infinite, okay, we covered. What's 6.2? Finite, okay. 6.1. What's 6.1? Oh, 6.1 is decimal as mentioned. So it's decimal as mentioned. Finite continuous, infinite continuous fraction, infinite continuous fraction, which is periodic. That is the quadratic irrational. Yeah, I guess for these two, the whole chapter, right? I think you just remember this is enough. Enough for you to do all the question already. The summary that I gave you at the start of this thing here. Again, make sure you know how to apply this formula to work out your decimal thing or to work out your okay. Any questions so far? No? No? Okay. So how about we break again? Let's break until 11:46.
下次就是30号是上什么？因为在我12点课，我现在走一下。
哦，可能会上一点点 chapter 7了。今天不用签到，还有人在上。好，好。
哦，因为这么高，有现在跑动另外两个就是是，然后我们做吧，还是还有我去买一个实力，是为了这才是这样的，对吗？说这个东西，那个本身它是跟人类父母的情绪是呀，就是解决的，也是感觉，我觉得那个酒，对姐妹就唱的，有一个这样就是，跟他，感觉这个很多。对，这是那个问题，第三个口语在一起这个问题。 刚刚一个好像出故事的名字，老是出故事的好危险啊！我帮那个是我听看到。这个我这个其实不知道，这个片那个，我觉得什么后面去的？就是为了那种这个是生活的基本原则，就而且是因为这个问题的正那个 boss， 大 boss， 我在 boss 的头发中，也按在按住。20分，对，20公里。做什么呀？对吧？好的，都是大的。我干嘛是蜡烛的话会通透？你们等待因为一次啊，好的，没有这个，因为他们是我们没有去吃，有没有吃？然后我就给我8点等那些，然后看没有人讲话，我吃醉了。
你们又打球？
吃龙体验本早。
去哪里吃？啊，打完球去吃？
早上你来去吃，走
去哪里吃？
去帮忙这个。
哦，妈妈，
他去找饭，还找时政，早上6点上课，7、8点进打球上做。这样厉害啊！8点打球。
以前我们6点半打球，
不是，
场没有人嘛。
我是以前有那的，玩比较早，就是那个场给人家敲那个手啊，我就进去打球，给烂掉了。要我刚那边他们拿锤子打烂那个门，然后继续打球，真的没？真的，吓门神的，不是我，假就是你，不是我，不是我把。啊，对，这个星期是可以打的。
不能哦，有人来访问。我2点有空。哎，这样先。啊，下个 Sam， 你不是还有考试 week？ 考试你们有没有打？
是打，照打，星期4打是的。
对啊对啊，因为你们考试在拜2不是？我拜4应该有空。哦，你有另外一个在拜5啊？我就你们吗？你们在拜2，我拜4有空。
还是打，还是跟放弃一点
啊？
考试之前放手一下是。要没有？要。还是这个还是也是因为还是先变钱，fix 两点差不多，应该都是 fix 两点。
对呀。
用回答。7万的流量了。不是，我是美国的。让我会收入吧，那个公司，我收入多一个整体啊，11万。我的速度低，我因为这些考的速度，我因为这些我就是病好死。
谁？没有，那是中国的老师。中国这3个都不算错了，
两太点考虑法错了，奇奇怪怪，音乐在这里的考想，你不能把它做一个东西，然后再去给它上天，但是这样，原就是自我的研究。你怎么这么说？那个极限我小飞，包你。我小学太低了，差不多，现在差不多。
那这个很爱看，因为我觉得这个条例。
也是可以。在靠题之前。
关于爱里面女孩子有一群人，
我在这边，我在这边啊，你们这边那个里面，
我们要一种这种。美女，
我女在这边，
有人说我挺仙女嘛？
你的意思？
有 classmate here。
我女在这边，啊，我
跟警方现在第15分钟的事情。
OK，发生什么？
没有，PCM 的同学来。
我跟你讲说，我你没有打过，
我以为我进到球场了。
地板
地板像，确实。Okay. I'm not sure. Maybe we'll go pretty far on this topic. Actually, there's not much real content here because if you really want to do real content here, it will be big advanced than this talk. But then the recent development of number theory is really on this percent. Yeah, whatever you learn before is like few hundreds years ago already. Yeah, the knowledge is like few hundred years ago, the GCDs. Then this one is like maybe 100 years or 200 years, maybe 150 years. Yeah. From now. Maybe even less than that. Yeah, maybe even less than that. Okay, maybe 100 years. Okay. So as the topic suggests here is these are the non-linear diagonal. Okay, so what you have mentioned last time was linear conversion, theorem. And then you did do a little bit of non-linear diagonal equation by looking at the primitive and x to the 19 more something, right? X to 19. Okay. Linear here just means that the power here should be 1. But here the power of this x, y is 1. This can be both as well. Okay. Does that make sense? Why the same answer? So, okay. Then the first thing we want to introduce you is called the Pythagorean triples. I think this one is very familiar to you. A squared plus B equal to B squared is C squared. So these are the set of positive integer a triple that satisfy the following diagonal equation x squared plus y squared equals z squared. So this is also called diagonal equation. Previously, it's a linear diagonal equation. This is called a Pythagorean triple. Okay, it satisfies x squared plus y squared. If they are relatively prime, then we will call this triple primitive. Okay. Can you give me some examples of this triple? 35, very good. Okay, so 3 squared plus 4 squared should be equals to 5 squared. Okay, what else? 3, 4, 5. Huh? 5, 12, 13. You need to check. Huh? Yeah. Can you give something that's not primitive? Because all of these are primitive, right? Can you give something that's not primitive? Did you memorize it? No? Ah, very good, very good. Good example. Later we're gonna prove this lemma. 6 squared plus x squared equals to 10 squared. Okay. So Isaac said just multiply by 2 on this Okay, good, very good. Okay, good. Enlarge the triangle, very good. Okay, this is a way of thinking using geometry. Very good.
这些很
Huh? 整数. Yeah, have to be integer. Okay, very good. Okay, so do you guys know that these things have relation to triangles? These are the side that 90-degree right angle triangle can take. Did you guys know this? A square plus b square c
对
square.
对对，说要为了发展，
Uh-huh.
就把这个脑
This is not primitive. Yeah, and then these two are primitive. Okay. Okay. Does it make sense? Okay, sure. So let's do some lemma here. So the first lemma is, let's say we have a Pythagorean triple. Let's say the GCD of them is D. Okay, so meaning their greatest common divisor is D. Then if I divide everything by D, it's still a Pythagorean triple. Moreover, they are relatively prime. Okay, so it's a primitive. Is it obvious that they are relatively prime? I already take away their GCD. Is it obvious? So first statement, I would say that it is obvious that the GCD of x over d over d z over d are relatively prime. This one is around, okay? Because you take away the common divisor already, meaning what? You take away all their common divisor. There's no more common divisor other than one. Okay. Second, you need to check whether it satisfies the Pythagorean triple. Okay, you just need to compute. Okay, so you compute what is x over d squared plus y over d squared. What's this? This is just x squared over d squared plus y squared over d squared. But then this is just x squared plus y squared over d squared. But we know that x, y, and z are Pythagorean triple, meaning what? S squared plus y squared is equals to z squared. So z squared over d squared is exactly z over d squared. Okay, so satisfy the good. Good. Okay. Yeah. Yeah. This is the field that mathematics give you. It's very clear, very logical. Okay. Next, next is the thing that Isaac said just now. So we can do the other way around. So let's say we start with any. Okay, we start with any Pythagorean triple. If we multiply anything to it, literally anything, any integer, so dx, dy, and dz, okay, it's again a Pythagorean triple. Similar, okay, you just do similar calculation. There's nothing else you can do. You have to verify the equation. Okay, so there's nothing else you can do here. So, well, you just consider dx squared plus dy squared. Okay, what's this? So this is just d squared x squared plus d squared y squared. Well, you can factorize it so that you get d squared times x squared plus y squared. But xy is a Pythagorean triple, meaning what? The sum will sum to z squared. But then this is just dz squared. Okay, done. Okay, so this triple here, dx, dy, and dz will satisfy the equation x squared plus y squared equals to x. Okay, good. Okay, so if you take away GCD, then you will become a primitive Pythagorean triple. if you multiply any number into your Pythagorean triple simultaneously, it is again a Pythagorean triple. So if you put in the geometry form, right, multiply meaning what? You are scaling the length. You scale the length, okay, equally. Yeah, okay, you scale the length. But then you don't change the right angle condition. Does it make sense? Okay. What's this? Pairwise relatively prime. Shall we do this? Okay, maybe we could do this. Okay. So some maybe a bit boring properties here because these are ready for next theorem. So let x, y, z be a primitive Pythagorean triple, meaning their GCD is 1. Then there's more important condition, more strong condition is that actually pairwise relatively prime. So last time we talked about mutually and pairwise, right? And pairwise is stronger. Because 2 by 2, their GCD is 1. Okay, so how do we prove this? Well, what we could do is we can prove by contradiction. Okay, so we prove by contradiction. So meaning suppose that x, y, z is a primitive Pythagorean triple. Okay, we can't really verify every cases, right? So then in that case, let's say, okay, any two of them, okay, they are not pairwise relatively prime. Then we want to show there's a contradiction here. Okay, so what does this mean here? If the GCD of xy is greater than 1, right, that means what? There should be a prime. Okay, there should be a prime P. Not necessarily the GCD, right? Just any prime, okay, such that P, such that P can divide x and y. Okay, makes sense. Well, maybe even before that, it can divide the GCD of xy first because your GCD could contain some prime divisor. Okay, so that this one implies that P can divide x or y as well. Okay, so since P divide x and P divide y, then P should divide the linear combination of them. Okay, any linear combination, remember, in particular this one. Okay, we can divide ax plus by, but then you can choose your a to be x, b to be y in this case. But then this means what? This means that this p will also divide z squared. And p can divide x squared. But then, really important condition on p, p is prime. If you have a prime that divide a square, what does this mean? Okay, so this actually means that p has to divide z. Okay, p has to divide z. So maybe I can give you some examples here without proving to you. So like 2 divide 4, then 2 must divide 2. Okay, but then if you are not prime, right? For example, if 4 divide, let's say 16 is not a good number, huh? So let me try 36. Okay, it doesn't mean that 4 have to divide. 16 is not a square. Is it a square? 6, yeah. Okay, it doesn't mean that 4 have to divide 6. Okay, can you see what's going on here? What's going on here? So this divisibility here, right? When you divide 4 divide 36, right? The two. Let me write down. How you split the 36 here? It's 3 times 2 times 2 times 3. So when you use 4 to divide 36, the two factors of 2, right, is dividing the different factors of 36. Okay, but if it's a prime, you have to come from the same factor. So that's why if you have a prime dividing a square, you must divide one of them. Exactly. Does that make sense? Without proving to you, I give you examples to see. Okay, so we can conclude that P divides Z. But then this is a contradiction, right? Can you see the contradiction? What did we say? Contradiction. This is a contradiction. What do we have now? Since we have P divide X, divide Y, divide Z. This means what? The GCD of X, Y, Z should be at least P, which is not 1. Okay, no? Understand? Yeah. Okay, so this is contradiction. Okay, so you similarly you can show for S, Z, Y, Z. Doesn't matter because this X, Y can be any two of them. Okay, so all combination won't work. That make sense? Yeah. So similarly, we could do for Y, Z and X, Z. Yes. Yeah. Any question so far? Okay, so although we say that the GCD of X, Y, Z collectively is 1, really we are saying that each pair of them, their GCD is okay. More stronger, even more stronger. Okay, due to this Pythagorean triple property here. X squared plus Y squared equals X squared. So far, so good? So far, so good? Okay. Any question? Got question? Yes. Okay, bye. 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 Okay, see you next time. Okay. Any question so far? No? Can get it? Can get it? Sihan can get it? Okay. I'll make sure you get it so that everyone can get it. Huh? Or someone don't get it. Do you not get it? You get it? Okay. Anyone don't get it? Feel free to ask. Okay, check it again. Okay, good. Okay. Next part is a very interesting property here. So if you have a primitive, okay, Pythagorean triple, then X and Y must be one odd, one even. Did you notice that? If we go back here, if it's primitive, you see there's a mix of odd and even. But then it's always only one of it. 3, 4, 5, 3 odd, 4 even, and 5 odd, 12 even. Okay, so we can prove that. Okay, one of them is odd, one of them must be even. Okay, well, the proof is very easy after we establish this. Can you try and think about why? After we establish this, the proof becomes very easy. Try and think for a moment. What if it is both odd? What if it is both even? If it's both even, then their GCD must be greater than 2. So cannot both even. Can you argue why cannot be both odd? If it is not both even, both odd, then it must be one even one. Why is it not both odd? Something very tricky could happen here. Something very tricky could happen here. So okay, let's write down. So proof it cannot be both even. Otherwise, the GCD of xy will be greater or equals to 2, which is not 1. Okay, so it cannot be both odd either. Not be both odd either. Okay, why? So we use contradiction again. So in this class, there's a lot of contradiction because it will give you extra condition, okay, to work with. Okay, so suppose for contradiction that okay, so meaning what? if you cannot prove something is correct, assume the other is true first. Okay. If you can prove something wrong, then you can show the original statement. So suppose for prediction that x and y are both odd. Okay. So if it's both odd, what do you know about odd number? What do you know about odd number? It's 2k plus 1 for some k. But then what do you do after you square? What do you get? 4k square plus 4k plus 1. What does this mean here? Can you see that if you mod out by 4, the remainder is 1? Okay, so if both of them are odd, then their square should be 1 mod 4. Okay, so now the progress language become very handy because we just get so meaning it is a multiple of 4 plus 1. Okay, so this is what we really mean. But then what? Sorry, yeah, some of this too. Okay, so let's consider some of this too. So what does this mean here? So meaning if z square is equals to x square plus y square, this would imply that z square is 2 remainder 2 after divide by 4. So what is this? You go back to your preliminary group chapter. You want to ask about what? Is 2 a quadratic residue of 4? How many numbers you have to try? 0, 1, 2, 3. So do they square to 2? 1 square, 2 square, 3 square, plus 3 square, 1. None of them. So 2. So in other words, but the Legendre symbol, right? Legendre symbol 2 mod 4 is -1. There's no solution. Okay. So, but there's no solution to it. Contradicting that x, y, z satisfy x square plus y square equals to z square. Okay, see, do you see how we put things that we learn together now? Tell you some truth. Okay. Yeah. Make sense? Yeah. So this Legendre symbol cannot use formula technically cannot, right? Because this 4 is not a prime. Yeah, so this 4 is not a prime, so you cannot use the formula. Because for 2, you will have like plus and minus 1 mod 8, right? But that one is for odd prime. But here, this 4 is not for odd prime, so you should check by root force. Just check root force. 0 square, 1 square, 2 square, 3 square. You won't get 2. Okay, so maybe I can cite here, and maybe by brute force. Yeah, just check everything. Okay. Yeah, so far any question to this? Okay, so if you have a primitive Pythagorean triple, one of them must be odd, one of them must be. So the parity is different. I will say that the parity is different. Okay. But is it clear that in this case, the z square have to be odd? Is it clear? Because you're adding an odd number to an even number. It has to be odd. Okay? So the z square has to be odd. If z square is odd, then z, I think it should be odd. Okay. Right. Okay, for the next part, I think I'm not going to prove to you. Because next part, we're not going to prove to you, but there's some result here. So let r and x be relatively prime, positive integer. Okay, if there is a positive integer t such that rx equals to t squared, then they are relatively prime positive integer mn such that r equals to m squared and x equals to n squared. Okay. So do you know what this theorem is suggesting? So if you don't know, right, so try some numbers. Okay, so follow the condition and then try some numbers. So for example, you take r and x to be relatively prime. So the easiest one could be 2 and 3. Let's say this two number will divide some square. Okay, so the product of these two have to divide some square. So not divide some square. Is actually equal to some square. Okay, so this is not very convenient, huh? This two relatively prime guy, because 6 is not 6 is not square or something. Maybe since this is so restrictive, right, we can start with some perfect square. Any perfect square you want to try? 4. 4? Okay, sure, 4. Okay. In that case, can you split 4 into two relatively prime numbers? I guess it's just 1 times 4, right? 2 times 2 is not relatively prime. Right? Sorry? 4? 4 times 9? 4 times 9. So meaning you want to consider 36. So it's a 6 squared, 36. Okay, so then you split up as 4 times 9. This is what you meant, right? Okay, so maybe this word, because 4 and 9 are relatively prime, then it says that this 4 and 9 should be some square. So in this case, this 4 and 9 is really 2 square times 3 square. Now try more examples. Maybe we can think of another example. And you can start with perfect square. You can start with perfect square. Any perfect square? Maybe, is it 144 too big? Can we start with something like this? Can you split it into relatively prime? I think there's a lot of choices here. 3 square times 4 square, which is 3, 6, you say? Did you mention a different solution? Huh? I think there's more than one solution, I guess. I feel like it. I'm not sure. Do you have different solution? Is it not big enough to give second solution? Maybe not big enough. 4 是30 can? Huh? 2, 4, 2 and 6, right? Okay, so 4, sorry. Wait. Oh, you mean 2 square, right? 2 square times 6 square. What is it? 4 times 36. Okay, so what does this mean here? This means that when R and X is relatively prime, you kind of split your factors. Okay, you split your factors because, okay, first of all, you should imagine that the factors in 2t square comes in pairs. They come in pairs. Okay, they come in pairs. And then if this R and X are relatively primes, meaning you split up the factors inside t square into either in R or in X. Because they are relatively prime. You cannot split the factors that come in K into two sides, right? Otherwise that basically it's not one anymore. Okay. Is it okay? Yeah. Okay. Good. Okay. So the condition here is because GCD of RS has to be 1. Okay, they cannot share divisor. That's correct. Okay, good. Okay, from this theorem here, okay, turns out that we can prove this. Okay, so what's this here? So this is a kind of very powerful theorem here. So the triple, okay, of positive integer is a primitive Pythagorean triple with y even if and only if there are relatively prime positive integers. So you resort to another two relatively prime positive integer mn, but m have to be greater than n. I mean, you can arrange them. So m odd, n even, or m even, n odd depends, such that you can rewrite your x, y, z into these two numbers. So really, your x, y, z can be written as just m. For your x will be m squared plus n squared, and y is m equal mn, and then z equals to m squared plus. Well, what's the first thing you should do once I told you this formula? What's the first thing you should do? Check whether this is a Pythagorean triple. So means what? You square this, square this. Let's check whether it is equal to the square of this. Yeah, so this is the first thing you do. Then I think the hard part is to show that there exists this m. Okay, the hard part is about showing this m and n here. Yeah. The hard part is about finding this m and n. Well, instead of tell you how to find m and n in general, could we like try and work out some example and then try and find what m and n will work? For example, for 3, 4, 5 here. Okay. For 3, 4, 5 here, can you work out what m and n will work here? 4 and 1. Wow, so fast. Okay, very good. So, well, I mean, like, there's only few number you can pick and choose here, okay, to get these, because these numbers are pretty small. So there are just a few choices you can do. In particular, I guess this guy here, this guy is quite limited. Also, this guy is kind of limited. Okay, this guy I would say is limited if y, because if you take 1 square, it's already 1, 2 square is already 4, 3 square is, you don't need to consider anymore, it's much bigger than 5. So can you make 5 out of 1 square? It's just 1 square plus 2 square. 2 square plus 2 square is like already 1 square plus 1 square is like 2 cubes. So 1 square plus 4 square. Okay. So we could take 1 square plus 4 square. Sorry, 2 square. Yeah. So in this case here, very nice is 2 times 1 times 2 is 4. And then at the top here is 2 square minus 1 square. So meaning your m is 2 actually. So swap the position. Okay. Yeah. So this means here, these 3 numbers here, you just need 2 numbers. Okay, to build this 3 numbers. This is just a categorization for primitive Pythagorean triple. And their GCDs. Okay, does it make sense? Okay, you just need 2 numbers to control this triple here. So meaning actually you can relate this to some, I'm not sure it's bijective or not, but then you can use some mn to build this xyz. Okay, yeah, because you can check that this is always true. It will always satisfy the differential equation. X squared plus y squared equals to z squared. Okay, as long as you pick relatively prime positive integer, m greater than n, I think is always works. So do you recognize why they choose m greater than n here? Because they want to make sure this term here should be positive. M squared minus z n squared. I think if it's negative also doesn't matter, right? Because you are taking square. Do we have a positive condition on our Pythagorean triple? Oh yeah, sure. Okay. So you need positive integer. Okay, so that's why they emphasize that m have to be greater than n. So the position is important. But then the parity doesn't matter. Okay, anyone, but there has to be different. That's it. We have proven it. Shall we try one more and then we can finish the day? Okay, we try one more, then we can finish the day. Can we list down all the Pythagorean triples x, y, z with z less than or equal to 25? Yeah, let's try do this. Let me check. There be something wrong with this question. You done? You done? Let me see if this question got problem or not. How many you list down? 6? 6? You sure? Huh? You found 4? Just 4? Okay. How about the rest? How many you found? How about the rest? How many you found? Let me see if this question, there's something wrong. I feel like there's something wrong. Because if it is for 5, z less than or equal to 25, then it will be too big to do. Maybe I just want up to z square less than or equal to 25. I feel like I just need this. Otherwise, it's kind of, is it big? It's a big. 25 square is like very big. Huh? If I restrict to z square less than or equal to 25, can you see what's the choice here? Okay. Well, let me see. Oh, wait. I think it's 25. I think it's 25. Okay. I think it's 25. Okay, good. So I think it's 25 because this is based off the previous theorem. Okay. So, well, if it is z less than or equal to 25, right? But then you need to solve another. How do you get 25? So you need to ask So by previous theorem, okay, you need to ask how to write 25 as a sum of 2 squared. Okay, so what are the choices here? Well, there are really not many choices, right? You can do like, sorry, huh? 3, 4. Okay, 3, 4. Sure. Or 3 squared. Well, we have to do with less than or equal to, right? Okay, so we can hit 25. Okay, we could hit 25 by consider 3 square plus 4 square. Okay, what's the less than 25 one? Maybe 2 square plus 3 square. Yeah, I think I get the 4 that Shakib say. So something like that. And like this. Okay. You can try all the possibilities, right? So these are your well, I mean, you could get 1.1 plus 3 square, is it, as well? Sorry? So this is the point here. So here, why doesn't work? Both odd. Okay, so M and N here has to be in different parity. Okay, yeah. They have to be in different parity. Okay, good. But then this term will appear later. Okay, this term will appear as a Pythagorean triple. Okay, so let's see why. And then in this case here, so these are the 4 possibilities. But then from here, you can get your y, you can get your x's, right? Okay, using the formula, y is equals to what? M square minus n square, and then x is equal to 2mn. Okay, so you can work out what are these corresponding terms here. Okay, do you see familiar Pythagorean triple coming out? Okay, so the point here is to go back to the question. The question say, these all the Pythagorean triples, are these all of them? Are these all of them? Ask you a question. Is this all of them? Huh? You think yes? Okay. You go back and think what I proved for you, right? If you have a Pythagorean triple, what can you do to your Pythagorean triple? You can multiply by some integer. You can multiply by some integer. But did you realize that if I multiply some integer to one of the set, some of the set, it is still having z. It is still having z less than 25. For example, this one. If I apply, multiply 2 to this, I get 10, 8, 6. Okay, so from the first one, from 5, okay, from 3, 4, 5, we get that 6, 8, 10. What else? 9, 12, 15. Any more? Any more? Yeah, we can go a bit further. 12, 16, 20, and also 15, 20, 25 are also Pythagorean triple with z less than or equals to 25. Okay, but if you look at the multiple for the other spectrums, that will be greater than 25. Okay, so actually there are 8 of them. Okay. Another thing I want to observe that we see this 25 square we express in a different way. This 25 square here. Is it different way? Yeah. One is 24 square plus that square is 25. The other one is 15 square of the you could have 2 different ways to add up to the same square. Okay, so in total, there are 8 of them. Okay. Question? Any question? No? Okay, so if you get a Pythagorean triple, you take a multiple, it's still a Pythagorean. Actually, I didn't prove to you I exhaust all the cases, right? I didn't actually prove to you I exhaust all the cases, but I just use some tools to tell you that these are also. But then, yeah, to be sure, I have to like prove to you why these are. Okay. Let's see if I can add into the notes. Other than that, I think for this class, I want you to know that the multiple of Pythagorean triple is still a Pythagorean. Okay. Okay. So see you tomorrow again. Gonna see you every day this week. Huh? You are. Yeah.
的话，它其实不是说要
对，不要记住。
它也可以。
一可以啊，哎，一可以的，因为 GCD 的一没
这个
yes， OK， 啊哈啊哈 ，yeah， sign or it's okay. Today no need to sign. Yeah, yeah.
刚我放到别的课。
OK， 没问题，没问题。